voltage, resistance, current density, and electric field, power, Ohm's law, and resistors in series, and parallel. So that one is the focus of 27. Voltage, so some of the same stuff that we've seen before, voltage and electric field, and then the emphasis on resistance, current density, power, Ohm's law. Yeah, okay, cool. So we start with the definition of current. We can say current I is defined as the charge flowing through a wire per unit time. More specifically, it's the derivative of the charge. So if there's a wire like this, so what you're doing is you're counting a certain cross-sectional area of the wire, how much charge is flowing through that area, right? How much charge is flowing through that certain spot per unit time, dq dt, the rate of charge flow. And it's units of coulombs per second, and it would be measured in ampere or amps, and the symbol for it is just capital A, amps. Okay, so that's the definition of current. So it's coulombs per second. So rate of charge flow, let's put it that way. Rate of charge flow through through a certain spot. Okay, then we can define current density, J. Current density is equal to the current per unit area. It's how much J is a current density and it's the flow of current per unit area. So then basically if there's a certain amount of current flowing here, then you would divide that by that area, right? And then that will give you the current density. So that would be units of amps per meter squared, or you could do centimeter squared or any other unit of area. Okay, so then that's current density. Then we're going to introduce something known as the conductivity of a material. Conductivity and resistivity. They're opposites to each other. Resistivity. Conductivity is sigma, the symbol. We can define that as, let's see here, J over E. That's kind of the definition. How much current density is flowing through a wire divided by how much electric field is required. So the way that the current flows is that you need a voltage difference between them, right? So let's say you need this side to be higher voltage and this side to be lower voltage, right? So it's voltage difference that drives current flow. So positive charges flow from higher voltage to lower voltage, right? So basically when we're saying current flow, the conventional current flow is the flow of positive charge. Even though we really know that if a positive charge is flowing this way, most likely positive charges don't flow. It's actually negative charges that are flowing the other way, right? But that has the same effect. Essentially, positive flows this way, it has the same effect as negative flowing the other way. So that's why it doesn't really matter. So that's why we can focus on conventional positive charge flow as being this way, from higher voltage to lower voltage. So this is conventional current, which is flow of positive charge. Flow of positive charge. Okay, so then the flow of positive charge occurs from higher voltage to lower voltage. And so then we're saying take the current density divided by the electric field. So the electric field must be in this direction, right? From the electric field is always from higher voltage to lower voltage. So this way. So the sequence of steps that happen is that you set up a voltage difference in a wire, and then that voltage difference creates an electrical field, right? Or you could even say it this way: you set up an electric field in a wire, so the battery is what sets up an electrical field, right? The battery sets up an electrical field, and then that electric field causes a voltage difference to occur in the wire, right? And then the current will flow this way from positive, from a higher voltage to a lower voltage, from a higher voltage to a lower voltage, right? So then we're taking how much current density is occurring there divided by the electric field required to create that current. So the lower the electrical field required to create current, and the higher the subsequent current is, the more conductive that material is. You see? So the resistivity will be opposite of that. It'll be letter rho, then it'll just be E over J. So then it'll be the bigger the current density. So in other words, hold on, let's see. I should put it this way: the lower the current density and the more electric field is required to create that, right? So if a big electrical field is required and the current density is low, then that means that's a very high resistivity. So that would be a good insulator, good electrical insulators. So high resistivity yields good insulators, but poor conductors. Good insulator, but good conductors. Good insulator, but good, yeah, good conductor.
But bad, right?
I should say bad conductors. Bad conductor, yes. And then if this is high, if the sigma is high, then that's a good conductor. And bad insulators. So the thermal equivalent of this would be the constant K, right? The heat conductivity. Usually if the constant K, if you're a good thermal conductor, you tend to also be a good electrical conductor. K and sigma are related. And then the rho is more related to the insulation, which was kind of like L over K, right? But rho in this case is not L over K, it's just rho is just 1 over sigma. It's just a reciprocal of sigma. So, but R is at least related somewhat to the rho. And then that would be same idea. So if you're usually like wood, if you're a good insulator, heat insulator, then that means you're also a good electrical insulator, right? So let's look at, what would the units of the sigma be now? Let's look at that. sigma. Okay, so J would be units of, let's see here, amp per meter squared. Amp per meter squared. And then the electrical field would be volt per meter. So that would be the units of sigma. And then the meter and the meter cancel. And you get here amp per meter volt. Oh, then we have one more definition that's going to come, which is the Ohm's law. So then we're going to say volt is current times resistance. V is IR. Again, when I say V, I usually mean delta V. So that means it's the voltage difference between the wire. So then that's V, and then current is the current flowing through there, and then R is defined as the resistance. So you can almost think of this as like this way. R's definition of R is dV/dt. It's the how much incremental voltage you get, and how much voltage, incremental voltage increase, and the subsequent current that is created. You see, so depending on if it's a good resistor, high resistance, then you need a high voltage to create a small increment of current. You see, so then R is dV/dt. It's the derivative of voltage. Anyway, so then the units of the R would be what? See, this is volts, this is amps, and then R is known as ohms. It would be R is ohms, and the Greek symbol omega is used for that. Omega. Ohms for omega for ohms. Okay, so then that's why I say the sigma is amp per meter squared over volt per meter. Then you get amp meter volt. But then here we see that amp over volt is going to be 1 over ohms. So this is going to be 1 over, right, because this is amp and this is volts, right? So if you do amp and then this is ohms, right? So then if you do amp over volt, is going to be, this is going to come down here, and then the ohms is going to go to the other place. So 1 over ohms. So amp over volt become 1 over ohm meter.
Professor?
And then that's the units of the conductivity. Yes.
Oh, yes. Okay, so sigma is conductivity, right?
Yes, it's conductivity.
Thank you.
Yep. And then the rho is resistivity. So then it's just a reciprocal of that. So it's kind of like you're defining a bunch of things. What is current? What is current density? What is conductivity? What is resistivity? And then again, what is resistance? And then what is, and then your unit. It's kind of like logical definitions, but we haven't really proven anything per se here, you know. Meter. Oh, no. This one should be, this one is already omega to the -1, meter to the -1. And then when you invert it, you just get, yeah, good catch. You just get the regular without the -1. Okay, so this is the resistivity coefficient. And then I'll tell you what the temperature coefficient is in a second. And then this is the conductivity. But then these are usually given at 20 Celsius. I think with thermal conductivity, the temperature was 25 Celsius. Right, yeah, 25. And then for these guys, the default is 20. So let's say, for example, copper is a typical one we use for electricity. So the conductivity, the resistivity is 1.724. So let's write that down. Copper resistivity is 1.724 times 10 to the minus 8. And then the units of that is what? Ohm times meter, right? Which is what we just wrote. Daniel corrected me. Okay, cool. So now this one would be the opposite of that. So it should be reciprocal. And that would be 1 over ohm meter, right? So sigma 0, 5.95 times 10 to the 7th. So ohm meter. And now the alpha coefficient of copper is 4.29. I'll tell you what that means in a second, times 10 to the minus 3. So now if we go to a different one, I believe silver is one of the highest conductive materials. It might even be the most, yeah. So for silver, so this is copper. Its rho 0 is 1.59. So I'm focusing on this now. Times 10 to the minus 8. Sigma 0. And then alpha is 6.1 times 10 to the minus 3. Now, on the other hand, those are like two good conductors. If we go to like something, let's see here, these are probably those were like metals. Of course, we would assume that metals are going to be, let's say, something like resistivity of wood. Glass. You see, so they're giving you a range. So you say wood resistivity is 10 to the 3rd to 10 to the 4th, and then glass 10 to the 11th to 10 to the 15th. Okay, just to kind of compare. Okay, so you see here, we've got the copper, 1.724 times 10 to the minus 8. So that's the temperature. We call that rho 0. That's the base that's the base resistivity at 20 Celsius. Ten to the minus 8. So if you reciprocate that, just basic reciprocal. 1.724 times 10 to the power 8 negative, and reciprocal, then you should get this. Oh, it's not quite coming out. Because that should be simply the reciprocal of that. But let's see.
Maybe it's rounded.
Yeah, maybe it's rounded. Yeah, it could be that it's rounded. Then you have here 3, 6, 7. Yeah. So in terms of the power of the 10, it does come out. And then here, if you have 1.59 times 10 to the power 8 negative, then reciprocal. Oh, that's better. Yeah, I see 6.29. Yep. Then you have here 3, 6, and then 7. Yep. Okay, so simply, this is just simply the reciprocal of that. So you can kind of see resistivity is very, very low, 10 to the minus 8. Then silver is even lower. So this is the best conductor. I believe it is the best conductor on the periodic table. Best electrical conductors. Or at least one of the best. So this is the lowest, which would mean this is the highest. You see, it's higher than that. And then wood, you can kind of see the range of the row. So that means the row of the wood is much, much bigger than this. So that means it resists electrical flow 10 to the almost 10 to the 11th, 10 to the 12th times as much as copper does. So we can kind of say it this way. Trillion.
The reason we don't have sigma is because for wood and glass, because they're not good conductors.
Well, we could have looked it up. I'm sure. Let me see here. We could have looked it up. Yeah, there it was. It's just the reciprocal of this guy. Yeah. You know.
Got it. Thank you.
Yep. So we can kind of say it this way. They are about a trillion. Wood is like 1 trillion times worse conductor than like copper or silver. Just by doing power of 10, because 10 to the 4th divided by 10 to the minus 8 is 10 to the 12th, right? 10 to the 4th divided by 10 to the minus 8. In other words, the order of 10 that you have to go from here to here is 10 to the 12th orders. So trillion times worse conductor. And then if you go to glass, its resistivity is very high. Electrical resistivity. So, oh my gosh, so it's even much, much worse electrical conductor. But thermal glass is a good, actually, glass is a good thermal conductor, but really, really poor electrical conductors. So we could say glass is a, I'm going to say okay thermal conductor. It's not the highest, but it's going to say good thermal conductor. Which is why you don't want to put hot coffee in glass, right? Good thermal conductor, but really poor electrical conductors. Okay, now where does this concept of the alpha come in? The alpha tells you at what rate the resistivity increases as the temperature increases. So it's the rate of it's 1 over Celsius is the units. It's the rate at which the resistivity goes up. So you see here, the resistivity of the silver is lower, but it's more sensitive to temperature variation. If I start heating it, the resistivity of the silver is going to go up, and it's going to catch up to the resistivity of copper because the alpha of copper is lower. So we could even ask a question, at what temperature will the silver and copper be just as conducting or just as resisting, you know? So we could kind of find out. So the formula is rho as a function of temperature is equal to rho as a function at 20 degrees 1 plus alpha T minus 20. So since usually the rho 0 is given in data tables, it's given for 20 degrees Celsius. So then that's our base temperature. And then the alpha is telling you at what rate the resistivity is increasing. And usually it's linear. As the temperature of the object increases, the resistivity of the object increases linearly, like that. Okay, so we could actually start with that one example